Okay, so the next talk is gonna be done by Nicole, right? And this is on HDDLGym, a tool for studying multi-agent hierarchical problems defined in HDDL with OpenAI Gym. Yes. So, yeah. So,
Much. Hi everyone, my name is Ngoc. I will be presenting the work about HDDLGym, a tool for studying multi-agent hierarchical problem defined in HDDL with OpenAI gyms. This work is collaborated with Ruaridh Mon-Williams from University of Edinburgh and Julie Shah, my advisor at MIT. The motivation is that the OpenAI Gym is a well-known, established, standardized interface for studying reinforcement learning. I guess you might be familiar with this diagram from previous talks. Another little new information for some of the people in this room is the HDDL, which is a hierarchical domain definition language. It's a well-supported structural language to encode hierarchical strategy. And also, it comes with a well-known support IPC list of all domain and problems that we can use to study hierarchical domains. And the idea is to combine them two together, and we hope that the HDDL gym system will support studying reinforcement learning with hierarchical planning problems. A little bit background in the HDDL is a hierarchical extension of PDDL. Simply put, this is a formalism to combine PDDL with hierarchical task network, also a well-known formalism for hierarchical planning in classical planning. Um, in addition, I assume that we all familiar with PDDL. So in addition to the action definition in PDDL, the HDDL also provide high-level action, which is task, as well as method is a way to decompose a high-level task into a list of subtasks, which is either a high-level task or a action. For example, in a transport domain, the deliver task can be decomposed into a sequence of 4 subtasks, get to a location to pick up, and then pick up the package, get to the destination, and drop off the package. Another different from the PDDL is that in HDDL, the problem goal is defined as a hierarchical task network as in this example. So, research gap, the idea of combining symbolic planning with reinforcement learning has been there for a long time. A very important word that related to our word is the PDDL gym, with also similar concept, but now connecting the PDDL with OpenAI gym. However, with hierarchical task network, is had more complex with the task and method. Therefore, simply using the similar framework in order to study hierarchical is kind of infeasible. So we have to, that's why I would like to introduce another framework that works directly with HDDL. The idea of combining hierarchical task network with reinforcement learning also studied by Hawk and collaborators in 2010. This work mainly consider the reinforcement learning concept in order to improve the hierarchical task network planning. So it's more focused on still classical HTN planning instead of providing a framework for reinforcement learning in hierarchical problem. Therefore, we contribute to the field with the HDDL gym as a tool to combine or to feeding the HDDL problem, the domain and problems into OpenAI gym, that now we can study hierarchical planning problems in a reinforcement learning framework. There are 5 features of our system. The first feature is that we support a smooth transition and adaptation of the existing HDL5 into the system. We also support multi-agent collaboration. We also provide problem analysis about the complexity or any difficulty before jumping to the step of designing hierarchical reinforcement method, as well as training and deploy any RL policy that designed for particular domain and problem. Before going deep into each of the features, I would like to mention that this is a tool paper, and we also provide a tutorial notebook that available in the GitHub code as well, that hopefully help the user guide through all of the steps and how to use the tool better. So first is the step to adapt the HDDL5 into the problem. Before try to modify and adapt into our system, we also provide a language model power HDDL user interface in order to help user, anyone who not very familiar with HDDL problem and domain, or even familiar with the language but not very familiar with the domain they're going to work with. We will provide a tool in order to help them visualize, have a graphical visualization option in order to understand what is the hierarchical task network provided in the domain, as well as having the language model to have some sort of natural language interaction with to understand the domain better. This tool also connected with the HDDL solver that will also try to give you some example of hierarchical plane and how it's gonna be visualized and look like and what we would expect from the problem. And then in order to adapt into the HDLGym system, because we want to handle with multi-agent features, therefore we would like to make sure the user explicitly mention what objects in the type is particularly for the agent in order to identify what agents in the problem, as well as make sure to indicate the agent or mention agent in the action that related to the agent. Also, because all of these features actually supported with the HDDLGym, so if you go through the tutorial, it will make the process way easier than you might see in here that a lot of requirement, but in fact, it's kind of straightforward. The second features we support is the multi-agent collaboration. So not many HDDL domain and problem in IPC actually having the collaboration method or the strategy. Therefore, some of the if we want to interact or we want to study some interesting collaboration in multi-agent setting, maybe user need to do some sort of extra modification to the problem. For example, this is a transport domain that we're now allowing a modified or adding another collaborative strategy to deliver a package by now allowing 2 or more agents to actually complete the task. For example, the truck and the ship is now actually able to do the same deliver task by allow them to transfer the package in the 2 nearby cities. And with that, that is an example of the multi-agent collaboration setup. And also in our system, we also have the multi-agent hierarchical planning pipeline in order to support multi-agent searching for the hierarchical for multi-agent. Because when you talk about multi-agent, it had a lot of assumption that we try to mitigate all of the assumption in order to make the problem or the tool be more general as possible. So in this case, we let the agent, all of the agent have the same priority in choosing the hierarchical. Therefore, we have a special pipeline in order to make sure that is fair for all of the agents in coming to choose what hierarchy they want by first generate a list of all valid operators instead of asking each of agent in the for loop to have the entire hierarchies generated, and then the other agent will maybe have last priority because they do the generation later on. So we do this all in parallel until all of the agent reaching the complete the hierarchy, and of course the RS policy would act as a heuristic function in order to guide and to choose what's the combination work for each of the hierarchy layers. The next feature is the problem analysis. We provide some features to analyze the complexity of the reinforcement learning problem before jumping into designing what is the input and output or action and state space of the problem. We run some investigation on what is the space of what is the the action and potential action and observation space when we choose crowded predicate to be our observation space, or we notice that in this table we have example of the transport domain as well as overcooked. So overcooked is a well-known in reinforcement learning, but it's not very defined in any PDDL or HDDL. So we actually customize defined overcooked in the HDDL, and because there are a lot of complexity or a lot of complicated interaction or transition in the environment, we end up using a lot of predicate in order to encode any transition rule. Therefore, we notice that if we use crowded predicate in order to encode or use it as observation, it's going to be too much and the model will be too big. Therefore, we're also using alternative like crowded dynamic predicates, which is the predicates that only used to change the state space, and we're not touching with the static, which is like the predicate that more likely to use to define the state or maybe the map and etc. Similar idea to come into the action space, that whether we want to choose the crowded or the lifted of all operators, or just simply method or action, and maybe including some information about object when we use lifted. Another analysis for the problem is the search difficulty. We use the random exploration with the pipeline in order to analyze the problem difficulty, meaning that we let it run randomly, and we notice that we measure the successful rate for a lot of random run, and for those we notice that with the multi-agent, that number of agent is 3 or more, we end up with the 0% of success rate that indicate the risk of low quality data while we do a lot of exploration in training. So that's happened a lot in a long horizon problem or any complex problem that is hard to reach a success state. So sometimes the training will be hard in order to come up with a good solution in training. That's why this one will be a way to flag the user to maybe having some strategy to handle those type of things, or maybe way longer in training in order to make sure that it converts into the optimal solution. The next feature we offered is, now we all know about the problem. Now we come into the design, the hierarchical reinforcement learning method, in which that users can modify what they want to be the input of the reinforcement learning, whether it's going to be observation type will be the crowded or the lifted or any dynamic predicates. The output will be any crowded, lifted action. Is up to them to choose, because now they understand what is the the size of the action and state space. So depend on that, they will know better that what would be the proper one to choose for their reinforcement learning policy. As well as they can either choose the PPO or any type of, so the default in us is that we have the PPO and NLP, but it's also be easily open to other type neural network like recurrent neural network or maybe graph neural network. So with that, we go into the train and deploy our policy. In order to monitor the training process, we provide certain metrics for the training stability. We record the loss throughout the training cycle, and for the performance, we recording the cumulative reward, success rate, planning time, plan step. And this is an example of the evaluation metrics. Ooh, there's some typo, but anyway, for the stability, we noticed that the loss function for, this is the training of the transport domain for 1 agent, 2 agent, and 3 agent for the stability. And we noticed that there's some interesting peak in the 2 agent and 3 agents. That is explain the non-stationarity of multi-agent setting, because there are some of the not very static feature when we go to MVP. Yeah, thank you. And we also noticed that it takes longer time to converse for any model with longer or more number of agents. For the performance, we also provide for metrics and provide a plot in order to help users to monitor whether the model is actually converged into a proper, or the optimal solution or proper solution or direction. For deployment, we also use the same 4 performance metrics in order to capture or to evaluate the performance of the reinforcement learning model. In addition to that, we also provide a demo that how we embedded that into the overcooked domain. and then use the HDDL in order to plan for the high-level task, and use the A-star model in order to do the motion planning. And with all of the belief and hierarchical state of the two agents in parallel, to have visualize whether how they collaborate or how they doing independently. Discussion. So this work has certain limitation. The first limitation is that in this work, we simply assume that agents have full observation about the world state and other agent primitive actions, which is not always the case when it comes to multi-agent planning. The second limitation is the discrete and deterministic. This is not really a limitation about the reinforcement learning, but it's the limitation due to the HDDL domain and problem that define in a lot of the international planning competition. That is because HTN already complex, so that's why we rarely have non-deterministic and other continuous features in it. However, it can be a potential future work of us that we would try to add more feature to handle the HDDL in a more in the non-deterministic or any numeric planning. As well, it will explore more hierarchical reinforcement framework, for example, that using different model for different layers, or maybe having the symbolic planning or symbolic planner in order to handle the high-level layer, and more of the reinforcement learning to handle these lower layer of the action. We're also thinking about having the human in the loop by having human to define the strategy by themselves, because all of the strategy or domain is encoded in the HDDL, which is more friendly to user who might not very familiar with the coding, but maybe with the help from language model, they can actually modify and capture what they want and what the strategy would be useful, so that it will constrain the reinforcement learning space in the way that adapt to human needs. This is a table of what domains we included in the system currently. We would like to expand that as well in future, and working with more customized domain, because a lot of here is the domain from IPC, but I guess it would be more fair to trying to convert some of the reinforcement learning OpenAI gym domain into the HDDL, which is extremely difficult. We know that from Overcooked, but that can be some potential future work. Thank you very much. Yeah. Any questions?
So we do have time for a couple of questions. Okay.
Yes.
Thank you for the very nice talk. I have a question, maybe it's very trivial. So how do reinforcement learning options fit this framework?
Reinforcement learning fit into this framework is that currently the HDDL doesn't have like a numeric planning or any optimization, but we assume the cost for each action is one, or maybe the goal. That is how we do the reward. And the reinforcement learning in here is more like the reinforcement learning. If you look at my pipeline, it's more or less the model it is actually more or less a heuristic model in order to support in the hierarchical task network search. And also we can also leverage that, because in a lot of HTN problem, that if the HTN, the hierarchical task network model, is not complete, it is hard to find a solution, or it's impossible to find a solution. Because the reinforcement learning, we're able to flexibly, do the exploration that regardless, outside of the hierarchical task network. It can be also add into, make sure to fix the problem even though the domain is not complete. That makes sense.
Yeah.
Oh.
Is there any association between options in reinforcement learning and, for example, task?
Yeah, there are some, but with the previous or a lot of reinforcement learning, hierarchical reinforcement learning work, I observed that the option or any other hierarchical is kind of more like hand designed and hard coded into the Python pipeline or any other pipeline. So it just make it hard to modify or change or adding into that, as well as this option sometimes it's just give only one layers or very limited layers. That's why we choose to try to leverage the HDDL where it have more option to define the hierarchical, if that makes sense. Yeah.
I think you already answered my question, but let me ask anyway. So when you do reinforcement learning, you get a policy. So I was going to ask how that policy is used while actually the agent is then going ahead with its planning. Is it just taking the action specified by the policy, or it is still doing some forward simulation, some planning while during decision time?
During the what?
When it is acting at inference time, like when you have a graph and you're showing the rewards, that is just by following the policy, or that is by doing something else which also involves using the policy?
Yeah, that the graph I guess I show in earlier. This one is the policies is supporting choosing the so it's more or less like a more heuristic model that adding into this like hierarchical task network searching. Because the hierarchical task is like different from the freedom of reinforcement learning that in PDDL or any other planning with reinforcement learning, you choose any valid action regardless how there are many valid actions, so a lot of options to choose. With the hierarchical task network, it's actually constrained that into a smaller subset of that that lead into the solution. So reinforcement learning will also support choosing that in that smaller subset. Yeah.
Okay, so is there any other question?
Thank you, Nicole. What is the execution model of in the multi-agent setting? Are all the actions executed simultaneously, or is there you guys determine some arbitrary order?
There's no order, so they execute like at the same step. Yeah. So that is another level of complexity, because that is how it's act in the real life overcooked, as I demonstrate. But if with that, we do need to do a lot of combination, and it can explode very easily. Without a hierarchical task network, it's going to explode a lot. But maybe hopefully with a hierarchical task network approach, it will shrink the combination size so that now it's smaller a little bit. Yeah.
I have just one quick question, but in HDDL, you can also specify a number of agents, or is it something outside?
So the formalism of the HDDL original not. So that's why I have the step of adapting the HDDL file into my system by make sure to identify what are agents, like what are agents that define. So basically, you can simply manually define what is the agents and how many. So the number of agents basically find the problem file. So that is how I shortly modify
Types
that.
for
Yes.
like agents. Okay.
Right. Yeah.
Is there any other question? So then I think we can thank the speaker and.